So I wanted to thank, this is my first keynote address. I'm a little nervous, but I wanted to thank Tabor Communications and Engage Events for inviting me. It's really an honor to be invited to come up and share what we're doing at Rolls-Royce. So thank you very much. I think I'd also like to mention, those awards were group efforts. So the IDC Innovation Award was a team effort working with LSTC and Cray and NCSA and Procter & Gamble. So with that, so just as an overview, I'll talk a little bit about Rolls-Royce. What I really am going to focus on is high-performance computing and how it impacts our design cycle. And I'll talk about the current challenges. I'd like to highlight what high-performance computing has done, where it's brought us in the last 20 years, and then where I think high-performance computing is going to take the manufacturing industry going forward. And then I'll take a stab at how this flows into the enterprise. So I guess I'll start out. So first of all, this is really the first chart on every presentation that someone from Rolls-Royce gives. The car division was spun off in 1971. There were some financial problems. So yeah, there are no discounts, no loaner cars, no chauffeurs. I actually just recently sold my Toyota. It was a good car. So I got involved in high-performance computing. I came from Iowa State as a developer for our computational fluid dynamics. And we were at the forefront of using the high-performance computing assets that we had. We had several different machines, and it was time to buy a new one. We had been recently purchased by Rolls-Royce. Our company used to be called Allison Engine Company, the facility in Indianapolis. And so I got tapped, and I went through the process of putting together the capital scheme and talking to the IT folks and getting signatures and running this through our IT provider to run the project. And it was kind of fun. I've enjoyed it, and I've stood up several different clusters over the last 15 years since I've been doing this. So a little bit about Rolls-Royce. So we're not in the car business. We're mainly an aerospace company. We focus on power systems. So aerospace makes up 60% of our revenues in 2014. Land and sea makes up the other 40%. So our tagline is better power for a changing world. So in aerospace, we cover both civil and defense. We work on a lot of these projects in Indianapolis. So it's a large installed base. There are about 13,000 civil gas turbine engines flying with over 30 different types of aircraft. A lot of customers. On the defense side, 16,000 gas turbine engines on 24 different engine programs and quite a few customers that we service around the world. So talking a little bit about the gas turbine engine, this is really a neat gee whiz business. It's one of the things I really like. So just a quick overview. The fan is at the front. It compresses the air. It ingests about 3,000 pounds per second. You get to the compressor, which compresses the air 50 times atmospheric pressure. It heats up the air to 700 degrees. This is the temperature, so 700 degrees Celsius is the temperature where steel starts to glow. So if you were to look inside a running gas turbine engine or a rig, the back components are starting to glow because of the heat just from compressing the flow. So this is classical thermodynamics. As you compress, you also raise the temperature as you increase the pressure. The combustor, we dump in 7 pounds of fuel per second when it's at its design point, and it raises the temperature another 1,000 degrees Celsius. So 1,700 degrees or 3,000 degrees Fahrenheit coming into the turbine, which is above the melting point temperature of the alloys that we're using in the back of that gas turbine engine. So we have quite I kind of wish I had a chart on this, but there's really very elaborate cooling schemes used to keep those turbines cool. So there are internal cooling passages, there's transpirational cooling, there are lots of small holes on the turbine which bleed out the cooling air and create a blanket of cool air. And then we use some other technologies. There's ceramic coatings and other things to keep those parts serviced well. This is the Trent 1000 engine. This is the launch engine for the Boeing 787 Dreamliner. So to handle this kind of a challenging, complex engineering problem, we use a lot of modeling and simulation tools, predominantly computational fluid dynamics and finite elements. So those are the workhorses, and we have a couple of different clusters in-house, three different supercomputers today that service those types of applications. We'll get into a few more details here. So Rolls-Royce invests a lot in research and development. I'll tell you that it's not enough in software development and high-performance computing, but a lot is invested in developing the technologies. These provide a competitive advantage for us. So we have 600 patents. We have an extensive university pipeline. So we don't really do, as a smaller gas turbine engine company, we're not part. So there are actually 3 big engine companies that manufacture and sell large gas turbine engines. So we're really the smallest one, and we're not a conglomerate part of a larger organization. So we've got to be innovative and able to compete, and we have an extensive network of university technology centers that we work with, and we bring, so they tend to do fundamental research that we bring into develop the maturity of that technology and eventually get it into our products. So we do a lot of in-house software. We've got 3 main in-house computational fluid dynamics codes. And then we do have a couple of in-house finite element codes, but we also have a portfolio of commercial applications to meet niche applications. There are cases where we can't develop software for all the cases. So that's really driven by a need. I'm going to talk a lot about the different constraints in the design process. So we also have the constraint in how much we can invest and how many people we can put on software development. But at the same time, we think not only is it a technical benefit to have our in-house software, there's also a benefit in terms of, at this point, economics, because there's an advantage in having in-house software and being able to run at scale. So we'll talk about gas turbine engine design. So if you step back, and there was, so at the NCSA conference last week, we spent a good amount of time talking about relevant scales of computing. And one of the scales that really impacts the design process is the design cycle time. It's really not a scale of computing, but how you scale the time, how you meet project deadlines. So we have really a portfolio of different applications, from low fidelity tools to high fidelity tools. And we do one-dimensional analysis, two-dimensional analysis, as well as three-dimensional analysis, and then time unsteady, so you add a 4th dimension for time. And the high fidelity tools that we used 2 decades ago still get used in our design process. Instead of being run once or twice a day, we run them hundreds of times a day on our high-performance computing clusters. So these jobs get thrown into the queue. We have some workflows that help manage how those get run. And I've had to talk to the folks that run those, how they can run them on our cluster without clobbering the file system. So we use this suite of codes to look at the design space. So we're looking at the design space, and we want to use low fidelity tools to figure out things like how many blade rows we'll have in a compressor and a turbine, how tall these should be, how fast the turbo machinery should spin. There's a wide variety of design parameters, and so to narrow down that design space, we use some low fidelity tools. And then as the design process matures, we start using the higher fidelity tools. So this is computational fluid dynamics, and we're looking at a mid-span or mean line two-dimensional calculation to see how shocks develop. So the flow going through a compressor in the turbine is transonic. The tips of these blade rows are spinning faster than the speed of sound, so you have shocks that develop in the flow passages. We do a lot of work, three-dimensional design. So that's really the workhorse, but then we do a lot of calculations. This is really a growing area, is the unsteady CFD calculations. It's an order of magnitude more expensive in terms of its computational cost, but there's certainly benefits. And as we get to a more mature design in the design process, we bring in the higher fidelity, more expensive computational tools. So I think it's worth talking about the constraints. So really, Larry talked about this yesterday. There's a real tug of war between the different design constraints that we have. You want to make the gas turbine engine as light as possible so that you get better fuel performance, better fuel economy. If you reduce the weight, the stress in these components go up. So the guys that do mechanical stress would like to have thicker, stout blades. It impacts the lifing. So what is the life of these components? How long do they survive in the gas turbine engine before they need servicing? So efficiency, dynamics, these are thin, long blades. They're like cantilever beams, and they're subject to vibration. They've got vibrational modes. So aerodynamics, heat transfer, manufacturing. And what's not on there is cost. We do a lot of cost optimization in the design process as well. And these are, typically we've got specialists in each of these areas. And in a design process, it's an iterative process. We do aerodynamic analysis, the stress guys look at the problem, and this design, different design iterations circulate through the different groups to come up with improving the design, meeting the design requirements. So it's somewhat time consuming, it's labor intensive, and so there's pressure to develop tools that are faster, automate the process. In terms of computational fluid dynamics or mechanical analysis, so we talked about constraints. One of them is, we're limited on how much capital investment we can put into high performance computing hardware. So in the design process, we really size the computational analysis so that we can get results overnight. So we would like to add more details, but they are tuned really to get a good turnaround time so that the design process continues to march. There's a drumbeat and weekly design reviews, and so this is really just part of the process in meeting the design demands. Well, I was going to talk about, so I talked about the next chart ahead of time. So again, this is, the design process is just that. It's an iterative process, and it's a balance between meeting the design requirements and the time skills. So talking about mechanical analysis, there are actually about 25 bird strikes on commercial aircraft each day. And part of the reason is that aircrafts are located in these wide open spaces where birds like to settle, and certainly as they migrate, these are good places for birds to stop over. So plane taking off will startle birds, and sometimes they fly in front of an airplane about 25 times a day. So the FAA and the European Aviation Safety Agency have requirements. Before you can start flight testing, you've got to get through a couple of tests, certification tests, to show that you've got an airworthy jet engine, and that this is really to reduce risk. So FAR 33, the Federal Aviation Regulations, spell out what the requirements are. You have to do some physical testing. And they actually, we build an engine, and they take a bird specimen. I don't think that they use actual birds, but something that's representative in terms of the physics. And they fire this with a cannon at 200 knots into the engine, and it damages the blades. But we use nonlinear finite elements in order to determine, well, it's risk mitigation, really. So you want to make sure that when you finish a design that it meets the design requirements. So these tests happen at the end of a design cycle, and you want to pass the first time through to meet schedule. You've got to remember that at the end of a design process, we have customers that are waiting to put these engines on new aircraft and start flight testing. They have schedules to keep. There's a customer relationship that's at stake in meeting time schedules. And then, of course, there are customers waiting to bring these planes into service to cut their fuel costs. So this is done with LS Dyna, and you can see that we've got really reasonably good agreement. It's qualitatively very good agreement, but if you look closely, you'll see that some of the energy transfer that creates the plastic deformation in the blades doesn't exactly match, but qualitatively it's pretty good. And we also do some aerodynamic analysis to show that it continues to generate power at a lower thrust level so that the plane can turn around and land. Probably the most rigorous test is this fan blade off test. They call it blade shedding in Europe. So really a difficult test. So this, I like the quote that they had in one of the news articles. This test costs lots of millions of dollars. So it's expensive. It takes a new engine. We put it on a test stand. So the FAA and EASA requires that if one of these blades are released, they're attached to the shaft using an attachment mechanism. So if that fails for any reason, they want to guarantee that the casing of the gas turbine engine will contain everything, that there'll be no bits of metal that come out of the casing. So that's really to protect the integrity of the aircraft. If something like this were to happen, you want to make sure that the wings aren't damaged, that the fuselage is not damaged, that the passengers are safe. So it's a destructive test. This absolutely destroys the engine. The bird strikes, you replace the fan blades. It doesn't do damage to the engine. You can keep replacing the fan blades and do more tests. So this is really the big analysis case that we run in-house. And we do this with LS Dyna as well. What we're looking at here, well, in addition to containing all of the shrapnel from the blades being released, it creates a very strong unbalanced situation as this is rotating at 9,000 RPM. So this thing really shakes if you look for a video on YouTube. It's really interesting to see. But this is required to stay attached to the wing. So all of the supports and the pylons have to support the unbalance of the shaft and the rotor of this thing spinning around. So we do this large analysis late in the design cycle to make sure that, as we get ready for the test, it's risk mitigation to the program. We want to make sure that we can meet the design requirements. So we do a lot of analysis ahead of time to have a good sense that we're on track. We're going to pass the certification tests. But then also after the tests, we go back and do a lot of validation runs. So we're getting good qualitative results. There's still a lot of work to do in increasing the fidelity of these calculations. So this is actually, an engine. This is a validation case. So this is a case that's run post-test, and then we've tried to go in and figure out what can we do in terms of modeling to better match the test conditions. Then one of the other benefits of doing this kind of test, in a destructive test, sensors begin to fail. You have trouble collecting data, and this simulation actually provides additional insight into what's happening in these extreme events. So you actually get a lot more information than you can just by sensors. You're limited on what you can measure when you're doing destructive testing. So this is another picture of that. So when we do this kind of analysis, it's whole engine modeling. capturing the system performance and response to extreme events. And again, what we're trying to do is larger models, higher fidelity, more information to have better risk mitigation. So the goal of this really is to take this high fidelity simulation and bring it earlier into the design process. So the traditional design, so the red line represents traditional design. On the y-axis, you've got design maturity. And as you go through the design process, you're getting more confidence that the design that we're converging to is going to meet the requirements of the engine. And we'd like to bring high fidelity analysis and these larger computing models earlier into the design process so that we have this kind of maturity earlier. So one of the benefits is to shorten the design cycle. The other is to make sure that there are no surprises near the end of the design process. I mean, the real expense here is not the lots of millions of dollars in the test. The real risk here is that we have to go back and spend 2 or 3 months backing up and starting the design process over again with the entire team. So that risk to reputation, the cost of redesign is really what we're trying to mitigate in terms of the risk for bringing this advanced analysis earlier in the design process. So what has HPC done for us? What have you done for me lately? So we've made a lot of progress towards environmental targets. So the ICARI is, I forgot what the acronym stands for. It'll come to me later. So we've gotten a 12% reduction on specific fuel consumption between the Trent 800 and the Trent 1000. So as you go with different generations of gas turbine engines, there's significant savings in terms of the environmental impact, carbon dioxide, NOx emissions. We talked about airports. So we've got this urban sprawl thing going in the United States. They don't have quite as much land to work with in Europe. So you have major airports in Europe, and communities are built up around those airports. So they're very sensitive to the noise of these aircraft taking off and landing. So they've got really the most restrictive sound and noise regulation in the world over in Europe. So those are actually very difficult to meet. And so we're making good progress on reducing acoustic signatures of the gas turbine engines. It's a difficult problem. So the other thing that advanced modeling, 3D, computational fluid dynamics, and the mechanical analysis has done is it's helped us develop really the most efficient turbofan aero engine flying today. So this is the Trent XWB. It flies on the A350, generates almost 100,000 pounds of thrust, and the fuel savings saves $2.5 million in fuel per year per aircraft. Beyond this engine generates 50,000 pounds of horsepower, and to put that in perspective, a F-150 Ford pickup truck generates 350 horsepower. A Mustang will generate 450. So 50,000 is a lot of power that this is generating. A Formula One race car is about double a Ford Mustang, 800 horsepower, and a single turbine blade at the back of the engine generates as much horsepower as a Formula One race car. So where are we going to go from here? I really see high-performance computing and advanced modeling and simulation going in 2 different directions at the same time. So on the one hand, we're going to go more of a macro-scale modeling system behavior, multiple components, and then in addition to system analysis, that will also begin to incorporate as manufactured. So currently we do a lot of analysis on as designed, but when you go and manufacture something, there are slight differences, and they get reviewed, they get analyzed. We have a process to sign off if it's out of tolerance, whether or not you'll accept those components or not. But As designed manufacturing, looking at stochastic performance on the fleet in terms of how different manufacturing processes impact the performance of a gas turbine engine, and then also wear and tear in the field. So as these operate in different theaters, you can get erosion on the front end. In deserts, that sand ingestion really does wear away at the leading edges of the compressors and fans. So it changes the shape of the airfoils, and it impacts fuel economy. And then that sand goes through, it melts in the combustor, and it starts to stick onto the turbine blades. So the turbine blades start to accumulate that silicon. So we actually take those components and do blue light scans of engines that have been in service, and we're starting to do analysis on as manufactured and components that have wear and tear on them. So that's the one hand going up. On the other hand, we're also going to go down to more of the micro scale, understanding how material properties are impacted by the manufacturing process. So casting, cutting, forging, machining, those processes change the crystalline structure of the metallurgy, and they introduce residual stresses in those components. So it's important to understand how the manufacturing process impacts the stress on these components, what their impact to lifing is, and it's a very difficult scale problem and difficult to get your arms around. So it's really a multi-scale problem. So we've got some work to do in terms of moving forward. So if you look at this system performance, this is really a trend for the entire aerospace industry. The US Air Force has this concept of a digital airframe digital twin, where they look at integrated multiphysics, understanding how the life of the engine or the aircraft components and the different missions that they run impact lifing, and they're interested in how to better maintain their fleet, how to reduce maintenance costs. It's something that Rolls-Royce is interested in as well. And then along with that, so of course, data and high-performance computing are converging. We're collecting a lot of data. All of the engine companies are doing this. We collect telemetry, and we have sensors on the engine, and they phone home through a satellite network. So we collect engine information. One of the benefits is if you know that there's a part that needs to be replaced, it can be there waiting on the tarmac so that when the plane lands, if there's time, they can swap out that part. Or if they need to swap out an engine, the parts are there, they're ready to do the maintenance, and you get that airplane back in the air as quickly as possible. Airplanes don't make any money sitting on the tarmac. So collecting that data, anywhere from half a terabyte to a terabyte of data per flight, generates a huge amount of data. So learning how to manage that amount of data with the data analytics is another challenge, a big multidisciplinary problem. And then Rolls-Royce is interested in the same thing that the United States Air Force is. So we're looking at this higher fidelity physics to look at the entire system early in the design process and not wait until we do prototypes. So my last chart here. What are the lessons to be learned? So really these improvements in parallel scalability benefit the entire ecosystem, I think. These codes become more efficient, faster. Those code improvements. So you can run at smaller scales. You don't necessarily need high performance computing. You can run a lot of this analysis, smaller cases on the desktop. It gives you a little more flexibility. I think one of the lessons I've learned in working on trying to make improvements over the last 10 years is that this process requires a lot of teamwork. So you need domain specialists, computer scientists, I think you want to work with the IT folks in the organization, bringing in high-performance computing. There's lots of opportunities to learn. One of the things that I like about the role that I've got at Rolls-Royce. And then certainly the ISVs are part of the team, and we've got a close working relationship with a lot of our independent software vendors. And we've done a lot of work with LS Dyna to try and make improvements in the code. So that's one example of working with a large team to try and move things forward. So I do have one more chart. So thank you very much for your attention. I'm ready to take a few questions. Appreciate this opportunity to share with you very much.
You have the microphone.
We're out of time.
Great presentation.
Thank you very much.
Thank you very, very much. For your first keynote, it was superb. I thought your numbers and what you were showing on the cost of the test rigs were very interesting. Is that how you determine a return on investment for high-performance computing internally? Are you at liberty to, we don't obviously want proprietary information, but are you at liberty to share at all how you evaluate an ROI for an investment like this, particularly since you have companies that are thinking about sort of making that jump or maybe adding to what they have?
So, you know, when you do a capital scheme, you've got a page on costs, and you've got a page on benefits, and you've got this internal rate of return. So the cost part is easy, and looking at the benefits is really, really difficult So for us, every single scheme, so we call it a capital scheme in Europe, it's a capital project, but every capital project has to tie back to an engine program, and you've got to sit down with the chief engineer and get someone to sign off on the benefits. And so I will say that it differs. So as over the last 10 years, our approach to figuring out what our return on investment in has matured. It's sort of evolved over time. It's a difficult thing to do. So it has to tie back to a project. It has to be specific. It's difficult to say you're going to eliminate tests because you can't always. Some of these tests are mandated by the federal agencies. So, but we can eliminate, so in terms of what we claim as benefits, you can claim some test elimination benefits. So those are hard savings. There are some so we don't just do that full up blade shedding or fan blade off tests all at once. We do some rigs that are smaller rigs with so it's a single arm test is how they call it a single arm test. And we look at different attachments. So that's a relatively simple test. Sometimes we can eliminate one of those. The certification agencies are looking at simulation data as well. So on bird strike testing, we can do the large birds. So there are actually 3 bird strike tests that you have to complete: a large bird, a medium bird, and a flock of small birds. And you have to position one of the small birds out at the outer radius where it's most sensitive, and one at the middle, and then a random distribution. I think it's 7 birds for the flock test. So the FAA is willing to look at the large bird test and our pre-test calculations, and if we get really good agreement, there's some negotiation. We can eliminate maybe the medium bird and then so eliminate one of the 3 tests, but I mean, I don't think that we'll ever eliminate all of the tests. So sometimes there's hard savings. We like to put in, risk mitigation. This is what we're avoiding, but our financial director doesn't like those kinds of, they feel like it's a scare tactic, and they really don't like that sort of thing. So that's about what I can share.
Okay. It's John from Boeing Company. I think we're doing a lot of similar things.
Yes.
I just have 2 questions. So you touched something on this multidisciplinary analysis or simulation. So Are you guys still using HPC primarily for single discipline modeling simulation like CFD or finite element analysis, or?
So good question. So really the gas turbine engine industry, these lower fidelity so I think there's a really good understanding where in the gas turbine industry, where you can make approximations, where you've got to do more modeling and simulation. So the answer is we still do a lot of single discipline analysis. There's a fairly decoupled, so it depends. There's a lot of analysis that we can do where the physics are somewhat decoupled. There's not a strong coupling. We can use boundary conditions to approximate a lot of the multi-physics that you would have. So you can put in, you don't have to use adiabatic boundary conditions, you can do some other things to approximate some of the multi-physics that you have in the different components. So certainly in some of our preliminary tools, they're very multidisciplinary. So on the one hand, we've got tools that are lower fidelity in computational fluid dynamics, but they're actually a much higher fidelity in the thermodynamics. So there's a broad spectrum of tools, but we're also doing quite a bit of multidisciplinary. So aeroelastic analysis makes up a significant component of our computational space, and we're making strides towards better multidisciplinary analysis.
Okay, I have a second question. Is actually you mentioned about HPC and the data management side.
Yeah.
So in the aerospace industry, we've been managing CAD data pretty well, but we are not really managing analysis data very well.
Yeah.
I mean, if you guys have you guys looking into that, or?
We are, yeah, and I can tell you that in terms of modeling and simulation data and managing that, the most difficult thing is not storage, it's dealing with people. So the analysts want to keep everything, and we've got to mature the process and have a policy on what makes sense to save and what we can recompute. So there's a trade-off, and some people, it's difficult to convince, well, it's difficult to come to a consensus on, where that line is.
David Wabin, Nanotech.
Yep.
With your CFD analysis codes, have you found any benefit in using parallel file systems for collection of the intermediate results, Luster or GPFS?
Yeah, so we do use parallel file libraries. And I don't have any specific numbers in terms of what the benefits are, but so on the computational fluid dynamics, it's not terribly file I/O intensive. You read in the large data sets at the beginning, you write them out at the end. You can checkpoint, but if you're doing an overnight analysis, I would argue, there's little value in doing any checkpointing.
On your military programs for jet engines, do you do more extensive research and development on high performance and then feed that back into your civilian jet engine production?
I think in terms of the design methods, we're using a lot of the same design tools for both military and civil. So I think in that respect there's a lot of overlap. I don't know how to answer more specifically than that. So
material properties, stress. I imagine the military aircraft engine is under a lot more stress than civilian that's due steady state.
Well, so there are different design requirements. So the answer is, I think that our projects on material science, modeling and simulation, all of that really works on both. So I would say on the military side, they're more concerned about thrust than fuel efficiency. They've got different targets. And then certainly for civilian aerospace, it's all fuel economy. I mean, that is the main factor. Everything else derives from that goal. Well, and cost. It's always cost.
You talked about you have 31 university technology centers.
Yeah.
So I was wondering if you would be able to elaborate a little bit more in terms of your criteria of research that's done in-house versus research that's done with partners like NCSA, for example, or other university centers. How do you separate those two, and how do you manage that?
That's difficult to answer in a minute or less. I could say that the different university technology centers, each one is in a different discipline. So these university partners, there are long-standing relationships that we've had with these different partners, and they're focused. The university relationship is not a permanent one. I mean, there's certainly room to find new partners, and it's not a marriage that is bound forever. So.
Yeah, I was wondering if you're doing uncertainty quantification yet around your results, and also how you do verification and validation. Are you having trouble convincing people that your simulations are accurate?
So actually, the designers have a really good handle on the accuracy. So the verification and validation is done with rig testing. So we instrument a compressor rig, and so Purdue is one of our university technology centers. So we have a rig with them, and we instrument it, collect a lot of data, and we do a lot of simulation and look at where we're matching, where we're not. So there's a lot of attention. So again, all of this modeling and simulation, we've got to meet the design requirements, and you've got to have good confidence that you're meeting the design goals. And it's difficult. So there's a lot of empirical modeling in the turbulence models. We're not modeling all of the physics. There's empirical models in there. So it's difficult to get exact answers. It's sort of an art in terms of how you use these tools in the design process. I don't want to give the impression that it's black and white and that these codes solve all of our problems. They give a lot of information, and they help you distinguish between one design and another, but we're not getting absolute numbers in terms of what kind of performance. So in terms of stochastic, there's a lot of stochastic analysis. So we're doing three-dimensional. So this three-dimensional blade shapes have actually really benefited. I think one of the points I wanted to mention in terms of what high-performance computing has done for us, beyond the improvement in fuel economy and environmental impact, we've reduced rig testing. So whereas in the 80s, I think Pratt & Whitney had an article, they talked about running 40 rigs. In the 1980s, and on one of their more recent gas turbine engines, they ran 2 rigs. And we've gone from 30-odd rigs on a compressor design down to 1 rig, 1 compressor rig, when we're validating the codes and looking at the design space we're operating in. So that elimination of rig testing is a big cost savings, but even more than that, it shortens the design cycle. So there is a lot of this design of experiments. So when you're so we don't just run a single 3D design shape. We run dozens and dozens to explore really the design space. So it is stochastic analysis.
Todd?
Yes.
So I'm assuming with jet engines, warranty costs, the life of a jet engine is how many years? And
hey, that's a great question.
And the warranty costs, are you using this 1 terabyte of data, sensor data, to help reduce those type of risk in warranties?
So Rolls-Royce sells these engines with, they call it on-wing care. So we don't just sell the engine, we sell an engine and a service package. So it's free oil changes for life, basically, or for a specified period of time. So when we sell this, we sell a care package, we take care of all of the maintenance. So that's good for the airline in the sense that they understand exactly what their costs are in terms of propulsion and maintenance. It puts the burden on Rolls-Royce that when we design and deliver an engine, we're responsible for maintaining it. So the life and replacement parts, that comes out of our pocket. So we work hard to make sure that we've got reliable engines. So in terms of life, so these things, our oldest engine is the T56 engine. It's a military engine. It's 60 years old, and it's still flying today. We've redesigned the back end of that, the turbine stage. They call it the T56 Series 3.5. And its maiden voyage is coming up. It's going to fly in the National Oceanic and Atmospheric Administration's Orion P3 aircraft that flies into hurricanes. So they're going to start saving money with this new turbine in the back end.
So I have actually here.
Yeah, thank you.
So I'd like to know about a little bit environmental impact from CO2 or NOx types of gas outputs. So what Rolls-Royce is doing to reduce that kind of impact in the ecological system?
So my only experience is in our traditional gas turbine engines, and so a lot of work goes into trying to improve fuel efficiency. So we do burner rigs, and I mean that is really the main focus in the civilian market, is getting better fuel economy and reducing the generation of CO2. You can't completely eliminate it with traditional fuels. But you want to minimize that and then reduce impact on the environment by having cleaner burning engines, reducing NOx.
This will be the last question.
Okay.
I think I heard you say that you develop or maintain 3 different CFD codes. I'm just curious why you have invested that much into CFD codes when there are plenty ISV codes available.
So these codes aren't just the solver. So it's a system, it's a design system really. So it goes from the geometry creation, mesh generation, running the analysis with the particular kinds of boundary conditions and models that we need, and then post-processing as well. So it's really an entire design package to help the designers set up this analysis quickly and turn around the analysis as quickly as possible. On the one hand, I think we also feel by having an internal development team, we can meet, so we have control over the technology. It is for us a competitive advantage because we feel like we're getting better results and better, more accurate results. And then we have control over the turbulence models and how we try to improve agreement with the compute rigs that we're doing. We go in and we spend a lot of time thinking about near wall boundary conditions, the turbulence factors that go in there. So there's one advantage there, and then licensing costs are expensive. We've got an enormous number of jobs running at any given moment. So we run those codes very hard.
Todd, fantastic.
Thank you.
Keynote, first time ever. Thank you so very much. I think you'll find it somewhat amusing, and coincidentally amusing, that Eric here used to certify Rolls-Royce jet engines for the FAA.
So ladies and gentlemen, please thank Todd.
Thank you
What a
very
Great
much.
job.